Right now, the entire AI industry is bottlenecked by a single piece of silicon. Companies are spending tens of billions of dollars a year on it, governments are writing export laws about it, and it started life as a chip for drawing video game graphics. In the next few minutes, you'll understand exactly how a GPU works on the inside, how it runs thousands of threads at once, why artificial intelligence runs on it instead of your CPU, and who actually controls the supply. Let's start at the beginning. To understand a GPU, you have to understand the problem it was built to solve. Your screen is just a grid of pixels, a rectangle of colored dots. On a 4K display, there are about 8 million of them. To draw a single frame of a game, the computer has to work out a color for every one: lighting, texture, shadow, depth. Then do it all again, 60 times a second. A CPU would work through those pixels one after another. Even a fast one, doing them in sequence, is hopeless. You'd get a slideshow, not a game. But here is the thing that changes everything. Pixel 1 does not depend on Pixel 2. Every one of those calculations is completely independent. So instead of doing 8 million calculations in a row, you could do them all at the same time if you had hardware built for it. That hardware is the GPU. Put the two chips side by side and the difference is obvious. On a CPU die, most of the silicon isn't doing maths at all. It's cache and control logic, branch predictors, schedulers, all the machinery for running one instruction stream as fast as possible. Only a small fraction is actual arithmetic. On a GPU die, that's inverted. The control logic is tiny. Almost the whole chip is arithmetic. That's because they optimize for two completely different things. A CPU is optimized for latency, finish this one task as quickly as possible. A GPU is optimized for throughput, finish as many tasks as possible per second, and don't much care how long any single one takes. A sports car versus a freight train. In numbers, a modern desktop CPU has maybe 8 to 64 cores running near 5 GHz. A data center GPU has around 17,000 shader lanes running at under 2 GHz. Each one is far slower and far simpler. There are just thousands of them. The way I think about it, a CPU is one professor, a GPU is 1,000 students. Give the professor a hard proof and he destroys the students. But ask both to add up 10,000 numbers, and the professor loses badly. So they aren't really competing. Your CPU handles branching logic, your operating system, anything unpredictable. The GPU handles the same operation repeated across an enormous amount of data. Graphics, simulations, and as it turns out, neural networks. Let's go inside. A GPU die is divided into blocks. NVIDIA calls them streaming multiprocessors, or SIMTs, AMD calls them compute units. A big data center chip has well over 100. Each SM is a small machine in its own right. It has its own schedulers deciding what runs next, a block of shader lanes doing the actual arithmetic, dedicated tensor cores for matrix maths which we'll come back to, an enormous register file, and a slab of fast shared memory that threads use to talk to each other. Now, one important correction, because the marketing here is genuinely misleading. When you read that a chip has 16,000 CUDA cores, those are not cores in the CPU sense. A CPU core is independent, its own control unit, its own cache, running its own program. A CUDA core is a single arithmetic lane. It has no control unit. It doesn't decide anything. It gets told what to do. Put it together in one top-end data center GPU is around 132 SMs, roughly 16,900 shader lanes, 528 tensor cores, and 80 gigabytes of memory bonded to the same package. So how do you program 16,000 lanes? Not individually. You write one small function, called a kernel, describing what a single thread should do. Then you launch millions of copies of it. Threads are grouped into blocks, blocks into a grid, and the hardware decides where to physically run them. But the unit the hardware actually cares about is the warp, 32 threads locked together, executing as one. AMD calls its version a wavefront. You never really schedule a single thread. You schedule a warp. And this is the trick that makes the whole design affordable. All 32 threads in a warp execute the same instruction at the same time, on different data. One fetch, one decode, 32 results. That's called SIMT, single instruction multiple threads, and it's exactly why the control logic can be so small. One control unit drives 32 lanes. There is a catch. If your code hits an if statement and half the warp goes one way and half the other, the GPU cannot run both at once. It runs the first branch while the other threads sit idle, then the second branch while the first group sits idle. That's warp divergence, and it's why heavily branching code performs badly on a GPU. Now the genuinely clever part. Arithmetic is fast, a multiply takes a handful of cycles. But fetching data from memory can take several hundred. That's the real problem in modern computing. The maths is cheap. The waiting is expensive. A CPU attacks this by avoiding the wait. It spends an enormous transistor budget on caches to keep data close, branch prediction to guess what's coming, and out-of-order execution to find something else to do meanwhile. That machinery is most of what's on the die. A GPU does the opposite. It doesn't try to avoid waiting at all. Each SM keeps dozens of warps resident simultaneously. The moment one warp stalls on memory, the scheduler switches to another warp that's ready, and it costs essentially nothing, because every warp's registers are already sitting on chip. So a CPU timeline looks like work, wait, work, wait. A GPU timeline is simply full, there's always another warp ready to run. GPUs don't eliminate latency. They bury it under thousands of threads. That single idea is the heart of GPU design. Which brings us to memory. A GPU has a strict hierarchy. Registers are fastest and smallest, though GPUs have unusually huge register files because they're holding state for thousands of live threads. Then shared memory in L1 inside each SM, then L2 across the whole chip, then the big pool of video memory. The bandwidth numbers are the real story. A desktop CPU pulls maybe 90 gigabytes a second from system memory. A high-end gaming GPU is over a terabyte. A data center GPU using HBM is north of 3 terabytes a second. Roughly 30 times wider than the CPU. It gets that by physically restructuring the memory. Instead of chips scattered across a board, HBM stacks memory dies vertically, connects them with through silicon vias, and mounts them millimeters from the GPU on the same package. Shorter wires, and vastly more of them in parallel. But you only get that bandwidth if you ask for memory properly. When the threads in a warp read neighboring addresses, the hardware merges them into one wide transaction. That's called coalescing. If those same threads read scattered addresses, you get separate trips, and your effective bandwidth collapses. And here's what surprises people, for a lot of AI work the compute is not the limit. The chip can do the maths faster than memory can feed it. Most real workloads are memory-bound, not compute-bound. Which is why so much GPU engineering is really memory engineering. Now, tensor cores. A normal shader lane does one multiply and add at a time. A tensor core takes two small matrices, multiplies them together and accumulates the result, as a single hardware instruction. It is a unit that does nothing but matrix maths, extremely quickly. They also work at lower precision. Standard maths uses 32-bit floating point. Tensor cores support 19-bit TF32, 16-bit formats, 8-bit, and on the newest chips even 4-bit. Fewer bits means less data to move and more numbers processed every second. The effect is dramatic. On the same chip, standard 32-bit throughput might be around 67 teraflops, while tensor core throughput at half precision approaches 1,000. Roughly 15 times faster, for the one operation AI actually cares about. And you can get away with it because neural networks are not like bank balances. If your account says £1,204.37, every digit matters. A neural network weight is one small number among billions, all being averaged together. Being approximately right is genuinely fine. So why does AI care so much? Strip away the mystique and a neuron does something very simple. Take the inputs, multiply each by a weight, and add them up. Multiply, add, repeat. That is a dot product. Do that for every neuron in a layer at once and it stops being a pile of separate dot products and becomes a single matrix multiply. One layer of a neural network is, mathematically, one matrix multiplication. Which is precisely the shape of problem the GPU was already built for. Stack dozens of layers, scale to billions of parameters, run it over trillions of tokens, and you have modern AI. It is matrix multiplication at absurd scale, over and over. That is the entire reason this chip ended up at the center of the industry. But one GPU isn't enough. A frontier model's weights alone can run into terabytes, far more than the 80 gigabytes on a single card. The model physically does not fit. So you split it up. Data parallelism gives every GPU a full copy of the model but different training data. Tensor parallelism splits individual layers across several GPUs. Pipeline parallelism puts different layers on different GPUs. Real training runs use all three at the same time. And here is the expensive part. With data parallelism, every GPU computes its own gradients, and then they all have to be combined and redistributed so every GPU ends up with identical updated weights. That's an all-reduce, and it happens after every single training step. Which makes the interconnect critical. PCIe, the normal expansion slot, is far too slow for this. Inside a server, GPUs talk over NVLink at hundreds of gigabytes per second. Between servers you use InfiniBand or ROS, which is exactly the RDMA technology we covered in earlier videos on this channel. Because if the network can't keep up, your GPUs finish their maths and then sit there waiting. Millions of dollars of silicon, doing nothing. At scale, AI training is as much a networking problem as a computing problem. So who actually makes these? Here's the fact that surprises people: nvidia doesn't manufacture them. Nvidia is fabless. It designs the chip. The silicon itself is manufactured by TSMC in Taiwan, and practically every serious AI chip on the planet comes off TSMC's lines, including AMD's. And the tightest constraint isn't even printing the transistors. It's packaging, bonding the GPU die and those memory stacks onto a single substrate, a process TSMC calls CoOS. That advanced packaging capacity has been the real bottleneck of the AI boom. The memory comes from a different set of companies again. High bandwidth memory is supplied by just three: SK Hynix, which leads with roughly 60% of the market, Samsung, and Micron. When HBM supply is tight, GPU supply is tight. In the accelerator market overall, NVIDIA sits somewhere around 80% of revenue. Custom in-house chips like Google's TPUs and Amazon's Trainium make up a growing slice. AMD is now a credible second source, and Intel remains small. But NVIDIA's strongest asset might not be the hardware at all. It's CUDA. Nearly 20 years of libraries, tools, frameworks, and tutorials, all built around NVIDIA's platform. A competitor can match the silicon. Matching 2 decades of software ecosystem is much harder. And almost nobody buys these outright. A single top-end accelerator costs tens of thousands of dollars, so most people rent them by the hour from AWS, Azure, Google Cloud, Oracle, or specialists like CoreWeave. So the full chain looks like this. TSMC builds the silicon, NVIDIA designs it, the clouds buy it and rent it out, and you train a model on it. One chip, crossing 4 continents before it does anything useful. So, to recap. A GPU is thousands of simple lanes rather than a few clever cores. It hides memory latency by keeping thousands of threads in flight at once. Bandwidth matters more than raw compute. And tensor cores are what turned a graphics chip into an AI machine. If that made sense, subscribe. This channel is computer science, explained properly. Thanks for watching.